Welcome, happy Friday. Friday before Easter. First Friday of week one, not too many announcements at this point. I still don't quite have an assignment ready for all of you, so expect something to be assigned fairly early next week that will be due the following Wednesday. I think that's about where we are at the moment. Things will ramp up in the very near future. Don't expect the lull in outside of class work or even inside of class work to continue quite at this pace. But for now, I think things are fine as we are catching up and ramping up to where we will be for the rest of the quarter. Anyone have any questions before we dive back into some running time analysis? Off we go. Last time we were looking at this fourth example, and I believe I posed to all of you, we'll work on this and we'll come back and talk about it. So what did we discover with regards to this? Did we go over a solution to this?
We did, I think.
Did we? We did. Okay, here was a solution. Yeah, we did talk about this.
I think we're already on this, average.
Yes, that's the one.
It just loaded on the wrong screen. Excellent. Yeah, we were looking at this. I don't know what happened to this machine. All right. Yeah, we ended exactly right here. We're going to go into official Big O and Big Omega. I told you I have the memory of a goldfish. This is your first real example of that. This was 24 hours ago, 23 hours ago. So Big O notation is going to be the worst case analysis of an algorithm. We will refer to when we see that Big O, that tells us this is a worst case analysis. It may run in a better order than this for some inputs, but we know that this is the upper bound of how long this can take. It is an analysis of the worst form of the underlying data. What is the longest possible order this could take? We talked about theta. Theta means we know the exact order. It will not deviate from this order for any input. So the only time we would use theta of f means that regardless of the underlying input structure, the algorithm will always perform in this order. There may be a constant scaling factor. There may be a lower order term that gets added or subtracted, but that dominating term stays the dominating term regardless of the underlying structure of the data. So if we were using theta on some kind of sort, it would say it doesn't matter what the underlying data looks like. If the list is already sorted, runs in the same time. If it's sorted in reverse order, same complexity. If it's randomly distributed across the array, if the ordering is random, operates in the same order. Big O would be in the worst case order. So insertion sort performs the worst if the array is reverse sorted. So you would want to think about how long does it take when the data is in that order. So Big O gives that worst case running time. The way to interpret this in English, this algorithm will run in time proportional to this order, but it may also run in a lower order for certain inputs. Omega of f gives us the best case running time. So in English, this is telling us the algorithm cannot run faster than this order, but it may run slower at a higher order for certain inputs. If we want to convert this into something mathematical, it gives us a lower bound and an upper bound for the running time of the algorithm. So if you report both a Big O and a Big Omega, that tells you the bounds. The algorithm will run between this order and this order regardless of the input. Does that make sense? Any questions on tying this to a mathematical bound? Yeah.
What exactly is the Big Omega and O of that?
Or not, again, data.
Theta says it always runs in a precise, the same order regardless. The worst case and the best case are the same. It's this order. It's useful when the upper bound and the lower bound are tight on the same order. So I created these slides for data structures where we care much more about lists and analyzing the structures that are lists. It's worth going over just to see this applied to structures that we've seen before. I don't want to focus too much of this class on the structures that are lists. We're going to be focusing much more on algorithmic problems, but just seeing how we apply this to lists. This kind of complexity analysis can tell us which of different structures that we could use, we should use, given the constraints of the problem. So you could imagine asking the question, all right, a client has come to me and requires some structured data in the form of a list. Should I implement an array list or a linked list to solve this problem? So comparing each method of each of these list types, we have the add, the remove, the get, and the contains. Those are the four big methods contained within any list type. Since they adhere to the same structure that is the interface for a list, they have to implement both all of add, remove, get, and contains in order to implement that interface. But they implement them in different ways. Hopefully this is familiar language to those of you in data structures.
Yes, it is.
Good. So here are running times for add, remove, get, and contains between array lists and linked lists. The thing to point out here is that the linked list remove is only constant if we are given a reference to the node to remove. If we have to go find the node to remove, that is linear. So this table is assuming that we have that reference. And we can see how this maps to performance in real time if we look at something like this. Here is a performance test on a generic array list and a generic linked list based on the add and get and remove. And we can see the differences between the actual running times in terms of time. So we're taking this theoretical idea of asymptotic complexity and actually running it to see how does the theory map to the actual time that it takes. And we find that it is very proportional. But sometimes there are large constant factors on these, which scale that in some way. Any questions on any of this data or on anything else?
No.
So the kinds of questions you can answer here. When should we use an array list? What would someone need to come tell you about what they needed from a list in order for you to decide an array list is the correct implementation for their needs? Yeah.
If we're not frequently removing elements.
Yeah, you don't frequently need to remove elements, but maybe you need to get elements very frequently. Because what do we know about how an array list removes elements? It has to shift everything over to fill the hole that was made by the element that was removed, because it has to be tight in the same memory space. There's no gaps. There can't be any gaps. It's a contiguous space in memory. So a remove is a very complex ask of an array list compared to a linked list. And get, on the other hand, is a very cheap. We can access that in constant time because of that addition and multiplication. That's all we need in order to be able to get an element anywhere in the array list. So if a client comes to you and says, I need this data, once I build the data, I'm not going to be modifying the data at all. It's an access. It's going to be access heavy. There are going to be a lot of people who need to quickly retrieve elements from this data, but we're not going to be messing with the data after it's been initially constructed. Then you would want to implement an array list instead of a linked list. It will be faster over time, over what the clients are doing to this list. On the other hand, why would we use a linked list over an array list? Yeah.
Say, you're building a list. Trying to think of that. Like, it's a system where added remove constantly, you're not always from it. That's where like this would be optimal. The getting from it is work of removing.
Yeah, absolutely. So this does make that assumption that we have the reference to the object, but yeah, with a linked list, all we have to do is modify next pointers, next references from the preceding element and the next element. So because of that, that's relatively straightforward, especially in a doubly linked list, where if you have a reference to the element, you can just grab the previous, change its next to this element's next, and you're done. Whereas again, with an array list, you have to move every element that comes after that all the way back into place. And that is time consuming. So if once you have the data, we're going to be manipulating the data, but not looking at individual elements of the data. We're going to be adding to and removing from the data more so than we're going to be querying what's in the data. If we do that, then we use linked list over an array list. All right, we're going to dive into some practice functions. I'm going to give you some C-style syntax rather than some Java-style syntax, and your job will be, we're no longer interested in a line-by-line analysis at this stage. We are interested in what is the overall complexity of this piece of code. What is the running order? What is the asymptotic complexity? We'll have 5 of these, and they'll increase in complexity with each one. Historically, what you might have heard is when you see a loop, that means we're adding an order. We are multiplying. For each element of the outermost loop, we're running the innermost loop each time. That is only true if we're iterating that loop a number of times proportional to some input variable. So we'll have to look at that, and we'll see some instances as we go through these practice functions where some basic assumptions that you might make can fall apart. So take a little bit, talk to your neighbors, come to a consensus. And let's see if we can determine which order this runs in.
Based on results. That is definitely interesting.
Okay. There's nothing that you want.
Yeah, but something else is.
You know, there's
A little bracing.
Some guys are the best.
Sure. This time we are not looking at individual pieces of different lines of code. We're looking at an overall order for this. Kind of skipping that initial step of line by line. And I'm going to throw some curveballs. The purpose of these practice functions is to take what assumptions you might make at a default level and make you actually have to look at the line by line code to figure out what the runtime attribute is. So for this first one, we see nested loops. What you have learned about nested loops is that we multiply the complexity of the outermost loop with the complexity of the innermost loop. What might be different about this? Why might this break that typical case? Sometimes we have to take a little bit more, a deeper look at the line by line code to get access to the real running time of this code.
Maybe I'm thinking it's might not be too hard about it. Just remember when you were on just like Oh, they're frequently doing
The interlude.
sort of the same thing, you know, what I mean?
Breaks.
From what I thought.
Oh, right.
Yeah, that's so, I thought it's at the interlude. So, at most you get, I would be confused, but, I think. Very likely with. Visit the.
All right, let's bring it back together. What do we see?
Right off the big bill, formally as.
Yeah,
With that break statement, the break on first. That may as well just be.
yes. Yeah, typically, when we look at the for loop condition to figure out how many times this loop is going to run, this will run from 1 to n, whatever n happens to be. So this is going to run n plus 1 times, one additional time to check the bounds. And then if we just looked at the for loop declaration here, we would see from 1 to n. This would also run n plus 1 times, but as was mentioned here, this break statement, as soon as we run this once, this is going to break out of this loop. And regardless of how many more times this was going to run, it is immediately going to break back to that loop and loop this around. So this loop, even though it says it runs n plus 1 times in the declaration, in practice, only runs once each time. So that tells us we replace this n plus 1 with just 1. And so we get n plus 1 times 1 instead of n plus 1 times n plus 1. So you could incorrectly conclude that this runs in a quadratic complexity when in fact this is linear.
Yeah.
Any questions on how or why this is linear and not quadratic?
But I know.
All right. So we can't just look at loop declarations. We have to look at the line by line of the code. Must look at every line of the code to determine its complexity. You cannot make large conclusions based just on small pieces of information. Here's another.
Oh, I've seen this before.
I like how this function does absolutely nothing with count. We're going to calculate something and then we're going to just throw it away when we return. There's not even a return statement. Great.
Well, it's a void function, so it wouldn't work work like that, but I guess if you work different. Anyway,
Yeah, we don't do anything with that count. We just calculate it and then throw it away. Yeah,
Would this be at logins?
it depends on if we. So very close. It becomes the difference between log n squared and log squared of n. It is n log squared of n,
Yeah.
which is, yeah, I think that's what you meant.
Yeah.
Mathematically, they're slightly different. Why? Let's come to the conclusion as to why. So going on a line by line basis here, looking at the outermost loop, how many times is the outermost loop going to run? N over 2 plus 1?
Yeah, that's what I'm.
So that's in order n. We don't really need to know precisely exactly how many times. We just need to know, for the most part, the order of each so that we can multiply those orders together. Precisely, this will run n over 2 plus 1 times. But that's in theta of n. How about the middle loop?
Log in to multiply by.
Yeah, it's log n. What happens when we multiply something by 2 that is exponential? If we're curious the number of times something is going to happen before we reach a breakpoint, that's going to be based and scale on the logarithm. So if we have some table, we have n and 2 to the n, we would see 1, 2, 3, 4, 5, we see 2, 4, 8, 16, 32. So if I do something like say, j is 1, j is less than or equal to 32, j equals 2 times j, then how many times are we going to run the loop before we get to 32? That's going to be based on the logarithm of log base 2 of 32, which is 5. So if we think exponentially, we're going in this direction, 2 to the n. If we then take 2 to the n as our n and say how many times is it going to run, if this becomes your n, then this becomes log of n. You're just taking the inverse. So that's why this runs in complexity log base 2 of n. LG is log base 2, for those of you who are not familiar. How about the innermost loop?
It's the same thing.
It's exactly the same thing. Yeah, relying on the commutativity of multiplication, doesn't matter if we have 2 times j or k times 2, it's the same thing, same logic. So this is also in theta of log n. And when we have nested loops, we multiply their complexities. So n times log n gets us theta of n log squared of n. So what is the difference between, what does log squared of n mean if we're breaking this out? This means log n times log n. If we had n log n squared here, this would be taking the log of n squared, not the log times the log. This is the log of n times n. So it's an important distinction between which you mean and where that squared goes. So if you're multiplying logs, the squared should go on the log. I again apologize to the people who are way over there for all of my board work. Let me know if that becomes a problem at any point. Large classroom does not lead itself well into board work. Were there any questions on this before I erase it? Okay. Let's look at number 3.
Plus.
Would this be at square log n?
It would be. Let's give people 30 more seconds or so to come to the conclusion of why this is n squared log n.
Now, that's the interesting. And. Sure.
All right, how are we coming to understand this? Outer loop, we've seen this before. Outermost loop, I should say. This is gonna run n over 2 plus 1 times
Yeah,
to go from n over 2 to n, and then it needs to be n plus 1 for this to fail. How about the middle loop?
that one. Yes, j plus n divided by 2, so I feel like.
Yeah,
Can we simplify that to j is less than n over two?
yeah, Yeah.
Like j to the point.
yeah. I pulled some of these from the way that I have seen students in a 210 level class write logic, and seeing that it is equivalent, it's worth being able to read code that is not fully simplified or is not quite as easy to read. So this increases your code readability to just be able to say, what is this equivalent to? What is this doing? And as a code reviewer, you would probably want to, whoever wrote this code, you would want to identify this and say, this can be simplified. This can be made more readable. Let's make this make much more sense to the outside reader. But j plus n over 2 is the same thing as starting at n over 2 and going up to n. So it's exactly what this loop is doing. It's just written in a different way. It's going to execute the same number of times. Unless, of course, we needed j to be starting at 1. In which case, we should just stop this when j is less than or equal to n over 2. How about the innermost loop?
That's the log n.
Yeah, we've seen this before. So the main point of interest here is this middle statement and what that means. So this will run in theta of n, this will run in theta of n, this will run in theta of log n. So we get n times log n squared log n. How are we doing? We ready for a challenge?
Bring it.
All right, practice function 4.
Okay. Okay. Fascinating. That is a challenge. I like it. I like it. Let me think. Wow, so. Hold on, so. Let's see. Oh.
Spoiler for others. Like
Not exactly. Track. That is a challenge, at least I have a general idea of how it's working, but.
What do we guess? What do we have? It's a good guess, but it is wrong.
I didn't think so, I don't think that was the right answer either, so.
It is probably the best incorrect guess. How do we define log? How did we define log on the last couple of practice problems?
Well.
It was as an inverse of what? Yeah.
An exponential.
Yes, the
Yeah.
log is an inverse exponential. How is this growing? If we look at not how many times will this loop run, but how is the s plus equals I growing as we get the I plus plus? How is it growing?
It's being added to, not really exponentially multiplied.
On the first pass, what is I?
Let's see. 2? No, yeah.
Yeah, so I guess we should look at what s is, not necessarily. So I is gonna go 1, then 2, then 3, then 4, then 5. What is s on s starts out before the loop, so 0 passes through the loop. S starts out at 1. On pass 1 through the loop, what is s?
3?
3. On pass 2, what is s?
6.
On pass 3, what is s?
10.
So how is it growing? If we were to come up with a function for this, yeah, that is the correct complexity.
Wait, what?
That is the correct complexity of everything. This is growing at a quadratic rate because this is 1, this is 1 plus 2, this is 1 plus 2 plus 3, this is 1 plus 2 plus 3 plus 4. That would continue on forever. What is the sum of 1 plus 2 plus 3 up to n? What is the shorthand for that? Comes up in every single one of my classes. N times n plus 1 over 2. If you've never seen this before, the way that we come up with it is I'm going to take the 1, the 2, the 3, the 4, the 5, etc. up to n, and I'm going to duplicate this in reverse. What is the sum of the first column? N plus 1. What's the sum of the second column? N plus 1. Sum of the third column? N plus 1. All the way down to the sum of the last column, n plus 1. So if we sum this entire thing together, how many copies of n plus 1 do we have? N of them, so that's how we get the n plus 1 times n. What did we do in order to, what question are we trying to ask compared to the question that we answered? Yeah, we duplicated everything. We agree that the top half is half of this sum. The top line here is half of that. So we would just divide that by 2. So if anyone ever asks you, what is the sum from 1 to 10? 1 plus 2 plus 3 up to 10. You could do that in your head for each one of those, or you could go 10 times 11, that's 110. Divide that by 2, that's 55. That's your answer. If anyone says the same thing for 1 plus 2 plus up to 100. 100 times 101, that's 10,100. Divide that by 2, that's 5,050. Done. It's way faster, and your friends will wonder what they've been doing their whole life. Or they'll wonder what you've been doing your whole life to know that, but case in point. So this is quadratic growth. If we expand this out, this n times n plus 1 over 2, we just distribute. We get n squared plus n over 2. The over two is a constant, the n is a lower order term. We did this before, if we remember that one of the practice functions way back a few days ago was n times n plus one over two, that was in preparation for this.
I remember.
So this is quadratic growth. When this is growing at quadratic growth, we're not asking the question, how does S grow? We're asking the question, now, as S gets close to some boundary, how many times will this loop run? And just like with the logarithmic answer before, the answer is the inverse of the growth of this. So the inverse of the growth of a quadratic is a square root. It's the same as n to the 1/2. So this is not a typical related order of growth. When you see a table of orders of growth, square root of n is not usually in it. Because there aren't many functions out there that are in the order O of or theta of square root of n. But this is what one would look like. Any questions on any of this derivation? Anything I can clarify as to why this is running in square root of n?
Where did they place in the table in terms of speed?
Yeah, it's a great question. So is square root faster or slower than log? Faster.
Looks like you're, not that you're going up.
So we know we have O of 1, we have O of log n, and we have O of n. I think it's pretty obvious to say that the square root of n is between 1 and n. The question is, which side of log n is it on? Is it closer to 1 than log n, or is it closer to n than log n? We'll take a, well, who thinks it should go here between 1 and log n? Some people. Who thinks it should go between log n and n? A few more people. We almost split the classroom in half. That was interesting. Answer is, it is closer to n than it is 1. The reason is that log n grows, you can think of this in terms of what is, let's choose something that goes in straight. Log n would be 1024. And square root of n is easy to see at, what is an easy square? It gets us fairly close to that, 30 something. But basically you take the log of something that's there and 30 gets you to 900. We'll go with something like 32. 32, 33, something in that range.
Yeah, that's
It's
actually-
fairly close too, but I want to go the other way of the logarithm and say 2 to the what power is 1024? And it actually goes in very nicely and evenly. If you can think of 2 to the 10 is close to 1,000, 2 to the 20 is close to 1,000,000, 2 to the 30 is close to 1,000,000,000. That's where the overlap between base 2 and base 10 is closest. Gives you a place to kind of take the base 10 that you've learned all your life and map it onto base 2 a little bit. But the 1024, the log maps to 10, and the square root of something fairly close to that maps to something in the low 30s.
Actually 32 exactly, I checked myself.
Pretty close to 32. I don't think it'll be exact.
Actually.
32 squared is exactly 1024.
Yep,
Beautiful. My intuition does not lie to me.
yeah,
Beautiful.
got on my own calculator.
32 is a power of 2. That makes so much sense. 2 to the 5th times 2 to the 5th should be 2 to the 10th.
Yeah.
I'm smart.
Don't inflate your ego, because we're here to learn, not
Right.
to get not to get fed on our ego. Now, maybe
That is
we'll
very true.
continue.
That is very true. So, yeah, let's give you 2 to the 5th, 2 to the 5th, and 2 to the 5th, be 2 to the 10th. So square root of 1024 gets us to 32. 32 is larger than 10, so it goes between. That would be how you would get there. Questions on that intuition? Yeah.
Could you also just think of it as their inverses, like exponential is way bigger?
Yeah, since exponential is bigger than polynomial, you inverse them. The inverse of exponential will be smaller than the inverse of a polynomial. Absolutely. Okay. That one was fun. Not a typical order. That's why I like it. So don't try to map code onto something that you know or understand. Try to understand the underlying code. Eraser works so much better. Okay. Practice function 5.
Oh, yes. Oh, okay, okay.
Another challenge problem.
And if the remainder of that is 0. Okay. Fascinating. Let's know the first part. Makes too much sense. Is less than I squared. If statement that throws me off.
In fact, this one is so hard that the source that I pulled this from was wrong. I like it when that happens.
Okay.
It also shows that if you rely on the internet for everything, you will eventually be lied to.
Oh yeah, definitely. Yeah, you gotta learn how to discern which is true and which is false.
Hmm?
S.
And 0 is this. Yeah.
Yeah, that's kind of weird.
Isn't it?
It is. Well, 0 I can probably scale with that, but it wouldn't do much. Oh.
Have a guess.
Kind of, is it like something?
It's not N to the 9.
Well, I would do that just
times something.
There is an answer for which that function would be correct. But it can also be simplified.
Yeah.
It is not a very long, complicated formula. It is something that is fairly short and sweet.
You log in.
A good guess, it is not. N, good guess, but wrong.
Just saying.
It is not N cubed.
Is it n to the fourth?
We have an answer. It is N to the fourth. How can we get there? Let's make it make sense with the last few minutes of class. So outermost loop. How many times is this running? This one is the
N
straightforward
plus
one.
1 times, or just theta.
Yeah, it's gonna go 0 will less than N. So that's gonna run N plus 1 times. Great. J starts out at I and is less than I times I.
Which is I squared and
A bit of a challenge. What is I times I as this grows? So J is gonna start out at something that is linear and go to something that is quadratic. This basically turns into N squared minus N.
Oh.
And if you want to look at that from an asymptotic direction, we're going to get rid of the lower order term. It does not matter that this starts at I. Could start at 1 and it wouldn't drastically affect the runtime as this scales. So this loop is going to run in the order of N squared times. Even though I times I starts out being small, it is worth thinking that what is the sum of those squares as we get close to, it turns out that it's half of. So it is a constant factor as we get 1 squared plus 2 squared plus 3 squared plus up to whatever I happens to be. It can be up to N, so we get up to N squared. So it runs throughout each one of these, and if we sum them all up. I'm still looking for subconsciously erasers. How terrible is that?
raise on the floor.
On the floor.
Of course.
Gravity.
Alright, let me think. Yeah, then the last one. A lot of this is kind of easy, though. The if statement threw me off.
Yeah, so this will run up to N squared times. We don't need to sum this. So here we have an N squared. But we have if J mod I is 0, then we're going to go into this loop. So how frequently is J mod I 0?
Fairly.
As this scales,
It'll become less frequent, but probably about like n times or something. I don't know.
yeah, it's every N times in this N squared. So N, this would, instead of saying we're going to multiply this through, we're going to say now, if that is the case, if J mod I is 0, then we're going to go into this, and that adds an extra complexity then. Because K is going less than J, J is technically I squared, so this would add an N squared. Right, this would happen an extra N squared times, but since the J mod I has to be 0, this gets divided by N. Since this happens every N times on average. So N squared over N is an extra N, not N squared. And that's where the source gets it wrong. The source fails to see this if and treats this as quadratic by itself. So I can reveal what the source says and why the source says it and show you why the source is wrong. So this says executes J times, which is N times N, but that only executes every J mod I times. So we need to divide it by how frequently J mod I is 0. And since N is mapped onto I, J mod I will be 0 every N times. Does that make sense? I don't know if I did that justice.
I think it does make sense. Oh, yeah, I'm sorry.
Yeah. I attempt to pique your curiosity every once in a while, which tends to make class go way too fast. But I have 3 hours of downtime between this and my next class, so I want to extend an invitation for anyone who wants to come play or learn some Magic the Gathering. I also will technically have office hours, so I'll get people started by that and handle any other questions that you have. But also, Magic is fun. Come play some Magic.